We are on to section 3, looking at the meaning of atom formal charges and calculating the formal charge on each atom in a molecule or a polyatomic ion. When there are several Lewis structures that are possible, we looked at one in this last video, the most stable structure will be when the atoms have the smallest amount of formal charge and any negative charge resides on the more electronegative atom. So let's figure out how to find formal charge, and we're going to look at CH4, methane. To find the formal charge, we take the number of valence electrons, NVE is number of valence electrons, minus, and then in parentheses, we look at how many lone pair electrons there are, LPEs, plus half of the bonding electrons. Let's look at carbon, for example. Carbon has 4 valence electrons, and then we subtract. How many lone pair electrons are around carbon? None, plus 1/2 of how many bonded pair are there around carbon? There's 2, 4, 6, 8 bonded pair. So 0 plus half of 8, which is 4. 4 minus 4 is 0. So the formal charge on carbon is 0. Let's look at the hydrogens around it. Each hydrogen looks the same. So if I find the formal charge of one hydrogen, then that's the same for all of the other 3. Hydrogen has 1 valence electron, minus, there's no lone pairs, and each hydrogen has a bonded pair, which is 2 electrons. So half of 2 is 1. 1 minus 1 is 0. Each hydrogen has a formal charge of 0. Let's find the formal charges of each atom in hypochlorite, ClO, and ClO3. So ClO minus, right here, we're going to find the formal charge of chlorine. Chlorine has 7 valence electrons, minus 6 lone pair electrons. 2, 4, there's 6 electrons around chlorine that are lone pair electrons, plus 1/2 of this. In ClO, there's only 2 electrons that are in bonded pair. So half of 2 is 1, 6 plus 1 is 7, 7 minus 7 is 0. So this chlorine has a formal charge of 0. Now let's do this oxygen. Oxygen has 6 valence electrons, minus, there's 2, 4, 6 electrons that are lone pairs, and then again that one bond between Cl and O, so half of 2. 6 plus 1 is 7. 6 minus 7 is -1. So the formal charge on that oxygen is -1. Now the sum of the formal charges for that compound is equal to -1, which is what that polyatomic ion's charge is. Let's look at ClO3. Each of these oxygens look the same, so we're going to find the formal charge of one oxygen, and that will be for all of them. Oxygen has 6 valence electrons. Each oxygen has 2, 4, 6 that are in lone pairs, plus 1/2 of each oxygen has a single bond, so 2 that are in bonds. 6 minus 7 is -1. Each oxygen has a -1 formal charge. Let's look at the formal charge of this chlorine. Chlorine has 7 valence electrons. This chlorine has 2 in lone pairs and 2, 4, 6 in bonded pairs. So half of 6 is 3, plus 2 is 5. 7 minus 5 is +2. Now let's look at the overall sum of the charges. That chlorine is a +2, and then each oxygen is -1, -1, -1. So that's -3 plus 2 is -1, which is what that whole polyatomic ion's charge is, ClO3 with a -1 charge. Let's find the formal charge of the carbon and the oxygen in carbon monoxide. For carbon, we know carbon has 4 valence electrons. This carbon has 2 in lone pairs and 2, 4, 6 in bonded pairs. So that carbon has a formal charge of -1. The oxygen, we know, has 6 valence electrons. 2 are in lone pairs, 6 are in bonded pairs, so that oxygen has a formal charge of +1. Let's find the formal charges of each atom in cyanide and carbonate. Why don't you pause? We need to first draw the electron dot diagram. See if you can do that for A and B. The first thing I did when I was trying to make the Lewis structure was I looked at the electron count. Carbon has 4 valence electrons, nitrogen has 5, has a -1 charge, so add 1, that's 10 electrons. So I drew my carbon, I drew my nitrogen, and I started with the electrons all around it and figured out in order for them to each have 8, 1, 2, 3, 4, 5, 6, 7, 8, we had to have a triple bond, and then we have 10 total in the structure. Let's find the formal charge of carbon. So we have 4 minus, how many are in lone pairs? 2 plus 1/2 of, there's 6 in those bonded pairs. So half of 6 is 3, plus 2 is 5. 4 minus 5 is -1. And let's look at nitrogen. Nitrogen has 5 valence electrons minus 2 in lone pairs plus 1/2 of 6. We have the triple bond. Half of 6 is 3 plus 2 is 5. 5 minus 5 is 0. When we did SO3, we should have a structure like this. Each O looks the same, so we are going to take 6 valence electrons for oxygen minus each oxygen has 2, 4, 6 in lone pairs plus half of each oxygen has 2 that are in bonds. So half of 2 is 1. 6 minus 7 is -1. Each oxygen has a -1 formal charge. Now let's look at sulfur. Sulfur has 6 valence electrons also, minus this sulfur has 2 in lone pairs, plus half of 2, 4, 6 in bonds. Half of 6 is 3, plus 2 is 5. 6 minus 5 is a +1. And if I add up all my charges, a +1 and 3 -1s, I should have a -2 charge. Now recall back to a previous chapter where we found oxidation numbers for atoms. In chapter 3, we learned to calculate those oxidation numbers as a way to tell if a reaction involved oxidation and reduction. Are an atom's oxidation number and its formal charges related? Well, formal charges and oxidation numbers are calculated for different purposes. Oxidation numbers allow us to follow changes in redox reactions. Formal charges, like what we're doing here, provide insight into the distribution of charges in molecules and polyatomic ions. For example, if I have hydroxide, OH-, and I wanted to find the oxidation numbers, remember our one rule is that O is always -2 and H is +1, which would make sense because our overall is a -1 charge. Those would be oxidation numbers. If I look at formal charges, I calculate them differently, and I would say oxygen has 6 valence electrons minus, there's 2, 4, 6 in lone pairs, plus half of, there's 2 in a bonded pair. Half of 2 is 1, 6 plus 1 is 7, so 6 minus 7 gives me a -1 formal charge for oxygen. And for hydrogen, hydrogen has 1 valence electron, there's no lone pairs, and there's 2 in a bonded pair. So 1 minus 1 is 0, formal charge of 0. Add those 2 up, and I get that -1 formal charge for the sum. Can you determine the formal charge for each of these oxygens and the carbon in this formate ion? Did you get 0, 0, -1? What about the formal charge of S in SO3? Hopefully you got +2. Not SO3 2 minus, but just SO3. What about this one? What's the formal charge of N in nitric acid? Hopefully you got +1. We're going to connect this when we move on to this section about resonance structures. Equivalent Lewis structures that are the same except for the placement of electrons. When there's more than one Lewis structure that could be made, and the structure contains double or triple bonds. Resonance structures have the same arrangements of atoms but different arrangements of electrons. The actual structure of the molecule is a composite or a hybrid of the equivalent resonance structures. For example, let's look at ozone, O3. If I have O, 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 and each oxygen has 6 valence electrons and there's 3 of them, so we need to account for 18 electrons. Well, just by having 2, 4, now let's go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Notice that my oxygen's on the left is nice and happy, this one's happy, but my middle one only has 2, 4, 6. It needs 8. So it could either take electrons from this oxygen and form a double bond, or it could take electrons from this oxygen and form a double bond. Either one of them would work. So I can have a double bond on the right, shown there, or I can have a double bond on the left. That is called a resonance structure, when I could have either one of those. Now this shows that when I have a double bond, we know a double bond is stronger than a single bond, and they are shorter. That's why it's showing that. Can you draw 3 resonance structures for CO3 with a -2? This is carbonate, an ion that has 24 valence electrons, and SCN with 16 valence electrons. See if you can build 3 structures of each. Let's see what you came up with. If I've got carbon with 3 oxygens around it, I could have a double bond oxygen on the left O, the bottom O, or the right O. And for SCN, I could have 2 double bonds, a single and a triple, or a triple and a single. Any of those would satisfy having the 16 electrons or the 24 electrons and still having the same charge, and everybody still having 8 electrons. Let's draw resonance structures for the nitrite ion, NO2 minus. First, I'm going to do my electron count. 5 valence electrons for nitrogen. 6 times 2 is 12 for oxygen. It's a -1 charge, so add another electron. That should be 18 electrons. So I'm going to have N, O, and O. N is my central atom. I'm going to at least connect them with 1 and see where we're at after I add electrons. So that's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Notice the oxygens are happy, but nitrogen still needs another bond. It could take electrons from here and form a double bond there, or it could take electrons from here and form a double bond there, which are both of these structures. Now let's find the formal charge on all 3 of these, because this O does not look like this O, does it? So we're going to take the O that has the double bond first. This guy on the left has 4 in lone pairs. This guy on the right has 2, 4, 6 in lone pairs. The guy on the left has 4 in bonds. The guy on the right only has 1 in bond, or 1 bond, which is 2 electrons. So if we find those formal charges, the oxygen on the left has a formal charge of 0. The one on the right is -1. Let's find the formal charge for this nitrogen. Nitrogen has 5 valence electrons minus, there's 2 in lone pairs, and it has 2, 4, 6 in bonds, so it has a formal charge of 0. Add up all of our formal charges, and we have a formal charge of overall of -1. Let's look at the resonance structures for carbon dioxide and dinitrogen monoxide. CO2, we drew this before, and this was how we drew carbon dioxide, with 2 double bonds to both of those oxygens. But we could also have a triple bond on the left and a single bond on the right, or a triple bond on the right and a single bond on the left. So these are all 3 resonance structures of carbon dioxide. Notice, this oxygen still has 8 electrons, this carbon still has 8 electrons, and the oxygen on the right has 8 electrons. So those are all possible structures. N2O, again we have 3 different possible structures. 2 double bonds, a triple and a single and a triple. Now when it comes to which one is most likely going to happen, it's the one that has the smallest formal charges, and therefore if we looked at this bottom one, we could immediately nix that one out, because notice that this nitrogen has a -2 formal charge on it. Probably pretty unlikely. Why don't you see how you could draw HCO2 minus and see which one is not a correct Lewis structure of it. Hopefully you got this answer. So going more in depth to what I was saying, the way that electrons are distributed in a molecule or ion is called its charge distribution. So we're combining formal charge and resonance here. Charge distribution can profoundly affect the properties of a molecule. Examples include physical properties such as melting and boiling points, and chemical properties such as susceptibility to attack by an anion or cation, or whether the molecule is an acid or a base. There's two guidelines to use when describing charge distribution in molecules and ions. The principle of electron neutrality. Electrons will be distributed in such a way that the charges on all atoms are as close to zero as possible. If a negative charge is present, it should reside on the most electronegative atom. Similarly, positive charges are expected on the least electronegative atom. In electronegativity, remember, fluorine is the most electronegative. So electronegativity increases as we go to the right on the periodic table and increases as we go up a group. Looking at CO2, here's an example, carbon dioxide, where if I found the formal charges, which you know how to do, so I'm going to eliminate doing the calculations, but if I found the formal charges on both of those O's and the C, I would get a formal charge of 0, 0, and 0. If I found the formal charges on this structure, which is also a resonance structure of CO2, I would get positive 1, 0, and negative 1. Now, a positive 1 and a negative 1 still is going to give me an overall neutral compound, just like this is a neutral compound. But structure A is our more favorable situation because all of the formal charges are 0, and we want as close to 0 as possible. So if we can eliminate the positive 1 and negative 1, then we will. Let's look at OCN, the second structure, and we could write these three different ways, A, B, or C. And if we found the formal charges on each of them, here's what we're given. Negative 1, 0, 0, 0, 0, negative 1, positive 1, 0, negative 2. So right off the back, I'm going to cross off C. It is very unfavorable because that negative 2 charge is the biggest of all three. And then I'm going to say, well, which one of these, A or B, is more likely? The only difference is the negative 1 is on nitrogen here, and the negative 1 is on oxygen there. Well, let's look at oxygen and nitrogen. Put your fingers on oxygen and nitrogen on the periodic table. And I told you electronegativity increases as I go to the right, closer to fluorine. So oxygen is more electronegative, which means if there's going to be a formal charge of negative, it needs to be on oxygen. So A is the more probable, favorable situation. Let's look at SCN again. We drew this on a previous slide. We said that SCN, we could have a triple bond and a single bond, two doubles, a single, and a triple. And if we found the formal charges on S and C and N in all three of those resonance structures, this is what we would be left with. That negative 2 charge is the biggest negative or positive charge of all of them, so I'm going to cross that off. It's unfavorable. Then we can see we've got 0, 0, negative 1, and negative 1, 0, 0. So where would the negative be most likely on? The N or the S? Put your finger on N and S. Well, N is more above S, but S is further to the right. In that case, I would refer you to this sheet that's further on, and I would have you look at N versus S, and notice that S is 2.6 and N is 3.0. So N is the more electronegative, making my middle structure the more favorable structure, since N is more electronegative than S. If there's got to be one, this is the more favorable one.